Pat Langley presenting work with Edward Katz on motion planning and continuous control, continuing with our theme of high-level and low-level control that we've seen in earlier talks.
Thank you for your patience, and thanks for coming. This is joint work with Ed Katz, thanks to some collaborators and my funders. Briefly, for those of you who don't remember what a cognitive architecture is, it's a unified theory of the mind that specifies what stays constant across different domains, incorporates many ideas from cognitive psychology, and typically comes with a programming language that embodies the theoretical assumptions that you can use to build intelligent agents. Pug is an architecture that we first described in 2016 at the ACS conference. And it's somewhat different in that it has symbolic relations, but they're always grounded in quantitative descriptions in the environment. Those relations have associated utilities that can be used to reflect trade-offs among the agent's objectives. There are discrete skills, but they have associated control equations. And there's a process of mental simulation that creates trajectories over time to guide planning. In this talk, I'm going to report a recent extension, which we call Pug C, because it unifies, it's first continuous, it unifies the symbolic and numeric processing much more deeply. This is one of the motivating problems that drove this work. So the old Pug, if you gave it a robot in a 2D environment and it's trying to get to that target object, it could only do one thing at a time. It could turn, it could move forward. You had to tell it what the waypoints were, and then it'd have to turn and move forward again and so on. This is not how people maneuver. And what we wanted was something like this, right? A much more natural, smooth kind of motion. And so that's where you're moving forward and turning at the same time, things like that. So let me go over the architecture, and just so you know, this is an example of why you don't want to have short talks at ACS, because I'm going to go through a whole cognitive architecture, so hold on to your hats. Pug has 4 types of generic long-term knowledge structures. There are concepts which define relational categories and their associated attributes. They also have a degree of match associated, a match function that we call veracity. I'll show you that in a minute. There are skills. Those tell the agent how to do things by specifying control values, and those are linked to how well a target concept matches. There are processes which the architecture uses to predict changes in attributes given the current situation, including current control values. And then there are motives, and those indicate the utility of relations. Those can be conditioned on the situation. So the architecture uses these elements for conceptual inference, for reactive control, for heuristic evaluation, and for plan generation. It's a 5-layer architecture, so we've outdone MIDCA. So the lowest level is belief processing or conceptual inference, and conceptual knowledge structures play the key role there. Then there's, on top of that, state processing in the kind of decision making, and skills are necessary to do that. Then there's reactive execution in the environment or mental simulation. And if you want to do mental simulation, that's where processes come into play. And then there's motion planning, which is not the same as task level planning. Motion planning, like that smooth trajectory I showed you, and that's where motives come into play to evaluate alternative trajectories. Now, this looks like a pyramid because the levels they cascade. Each level uses results produced by the one below it. And this is similar to the older Icarus architecture that inspired this, but it's got more levels and doing richer processing. I'm going to go through some of the knowledge structures, but I won't have time to explain them in detail. This is what concepts look like in Pug C. They're a little bit like Prolog, except that there's always numeric attributes associated with these relational descriptions. And there's a match function. And that function that says linear, D, PQ, whatever, basically it gives you a degree of match, a little bit like what you'd find in fuzzy logic. So these are not probabilities. This is more like a typicality match. So for example, is the robot facing a target? Well, it can be facing it more or less. And if the angle is 0, then it's a match score of 1. If it's an angle of 20, then it's going to be less than 1. Conceptual inference is a bottom-up process. You match conceptual rules to infer beliefs, like a robot is R1 is at object O1. That involves computing values of numeric attributes. So higher level relations have their attribute values derived from the lower level ones, and also computing this veracity, this degree of match score. And this applies recursively, so the system computes the full deductive closure, which I know is not psychologically plausible, and we'll get to that next year. You can view, when the system is done, you can view the set of beliefs as a description of the state, and because each belief has a degree of match associated with it, you can view that as a point in an n-dimensional space, one dimension for each belief that you have. We don't really use that, but it's an interesting idea. So this is what beliefs look like. There's perceptions. Those are primitive beliefs that come in from the external world. And then there are inferred beliefs. These tend to be relational. And again, you see that these are only a few of these are matching with a score of 1. Others are matching less because they're not at the sweet spot. And there's this utility over here, which I'll tell you about in a little bit. These are Pug Skills. These are telling the agent how to do things, and there's apart from the name and the arguments, there's two important things here. The target, this is always going to be a defined concept that again can match to a greater or lesser degree, and then there's one or more control equations. This is a control variable, and this says that the value of this control variable should be 0.3 times the degree to which this target concept mismatches, 1 minus its veracity. That's going to give us an error signal. And so we can do something like continuous control over relational structures. Intentions, I guess they are misnamed here, but they're just instances of skills. This is the simpler, more classic notion of intention. For state processing, when on each state processing cycle, the system has a set of beliefs. It's got a set of intentions that it's going to try to apply. So it checks to see if their conditions are satisfied. If they are, it finds a degree of mismatch to that intentions, that skills target concept. If it doesn't fall below if the mismatch is really low, you just don't worry about it. But if it's above a threshold, then you insert that mismatch score into the control equations. That calculates the values of control variables. And if more than one intention applies, then you take the vector sum of them. And that's very similar to what you see with potential field approaches to robot control. These are processes. And you don't need processes to do control, but you do need them to do some more sophisticated stuff. So again, don't look at the details, but these are, think of these as the kind of process you'd find in qualitative process theory, but they've actually got numeric equations attached. So they tell you how things are going to change over time. Some of the variables here will be environmental variables. Some of them may be like move rate and turn rate. Those will be control variables. So the third layer is what I call reactive execution and mental simulation. So on each of those cycles, Pug applies the skills it has, the active intentions, and it invokes the state processing repeatedly to calculate values of control variables. It does this repeatedly, and that generates a motion trajectory. If the agent is carrying out actions in the environment, that's just reactive control. That does not require prediction. Okay? It doesn't have to predict future states. It just says, well, under this situation with these values, I'm going to calculate these values for control variables, and that's what happens. But if the agent wants to look ahead to do mental simulation, then it does need processes to predict what the next state's going to be, and then it can apply the same state processing stuff to that. So each trajectory. So for a given environmental situation and a given set of intentions, that is, instances of these skills, behavior is deterministic. That is, there will be a trajectory that follows. So, for example, these are from system runs. If you give it this initial situation where the robot is on the left, right here, and it's facing up in this direction, and it's trying to get here, it's got two intentions. It wants to move to O1, and it wants to turn to face R1. And it does them at the same time, and it just goes through and does this. Now, this is all mental simulation. It's not doing this in the world, although if you did it in the world, this is what it would look like too. If you have this situation where there are these obstacles, then if you give it these four intentions, you want to move to and turn to O3, but you also want to avoid R1 on the left, and you want to avoid, you want to avoid O1 on the left and O2 on the right, then you get this behavior. And again, these follow deterministically from the set of intentions and the initial state. So there's no search here, okay? We will call this a motion plan because it is a mental simulation of what's going to happen. But there's no search at this point. Now, how do you find those things? Well, you can give the system this, and it'll behave that way. But if you also give the system motives, these are basically factored objective functions, right? So you can have a set of these rules. Each rule says under these certain conditions, this belief, or this kind of belief, has this much value. There's two kinds of motives. There's achievement motives, which only give you utility the first time that belief occurs. And then there's maintenance ones, which give you that value every time that belief occurs. So for example, you would use that to avoid obstacles, whereas the first you would use to go to a target. So the system can construct motion plans using heuristic search. It combines mental simulation with these motives to guide that search. It starts from an empty plan. It has one or two target relations. It wants to, for example, it wants to be at an object and facing it. It retrieves intentions that would achieve that because they're in the target concept associated with the skill. And then it simulates it. And it for each belief on each time step, it calculates the utility. That gives you utility for the entire state. And that also gives you utility for the entire trajectory. If some of the beliefs in the trajectory have negative utility, that's a problem. So Pug goes on to retrieve more intentions that would help it avoid those. If there are multiple repairs, like you could say, well, I could avoid this on the left, or I could avoid this on the right. Then that's where search arises. And so it does greedy search in the sense that it always selects the alternative with the highest utility. And that continues until it finds an acceptable motion plan that is with no negative utilities, or it can't do anything better. And here's a simple example. Okay, here's a simple example. You need to be more vigorous. So the agent wants to reach this target object on the right, the blue one. Starts with an empty plan. It retrieves two skills, intentions. Well, just one, just to go there. That trajectory goes right through that first obstacle, so that gives high negative utility. It then says, okay, well, maybe I should add an intention to help. There's two options. You can avoid that obstacle on the left or on the right. It tries them both. They actually give the same utility score overall. So then it picks this at random, then it says, well, there's still a problem because it's running into this. So it then adds another intention to avoid that. And it turns out this one is better than this one because it gets there faster. The average utility is higher. So that's how so that's how heuristic search for motion plan works. And again, this is at the fourth level. Just to review, so Pug incorporates insights from earlier work on cognitive architectures, from error-driven feedback control and potential fields, and also a lot of ideas from qualitative reasoning and quantitative simulation, but puts them all together. One thing it does not do, it's not doing integrated task and motion planning. There's no task planning in the talk I have given. One of the reviewers had a real issue with this, insisted that this was task and motion planning. It's not. There's room for that. We're going to do that, but that's not what this is. The future work, we're going to add support for virtual objects that can specify places and larger scale topological maps. And I do want to hook up to the older version, another extension to Pug called PugX, which integrated task planning, execution, and monitoring, but that's for next year. And that's the summary, and I'll stop if you want.
Perfect, thank you. So I'll start with one from Slack, and then, I
don't have to change glasses.
Andrew asks, do Pug programmers really encode all these rules at this degree of detail, or is most of it learned?
None of it's learned. Why should it be learned? Is learning, so look, for those of you who have known me for a while, you know that I'm happy, I think machine learning is an important topic, but you don't work on machine learning until you first understand representation and you first understand performance. So we are not at the stage in the development of this architecture to focus on learning yet. So hold on to your, hold your horses, give us another few years and we'll get there. Next. Hey.
So my question is, what moment the agent will start questioning on its own beliefs? So sort of just realize my belief is wrong, or even on its skills, maybe it just somehow the skill representations.
You're assuming far more sophistication in the inference process than we have. So it is on every time step, whether it's in the whether it's doing things in the world or just doing mental simulation, it says, I've got these percepts or these imagined percepts, and it computes the full deductive closure of all the beliefs that follow from that. So it's done anew each time. So there's no, it's automatically reconsidering things every time. I know that that's not ideal, and it makes more. I've done some other work with Mohan Sridharan about how to do belief revision. And I would like to incorporate that, but we're not there yet. Mike? Uh-oh, he's going to get after me for the Midka joke.
I was wondering, it was interesting that you have this way of determining whether more or less are you facing a certain direction or something. So if it was a goal, and one of the operations we thought of is goal achievement, because is the block on the other block? It could be kind of wobbly and halfway on the block or something. Do you have ways of judging whether a goal is achieved? And would it differ depending on your deadline or whether you have a boss?
No, that's a good question. I'm glad you raised this question. And it's one of the ways in which Icarus and Pug differ from some of the more traditional architectures like SOAR and ACT-R. Goals are simply desired beliefs, right? So you can't, the only way to know whether you have satisfied a goal is to see whether the belief is true, right? That the corresponding belief. And if the belief is more true, then the goal is more nearly satisfied. And there's a threshold, right? I didn't focus on this aspect, but I mean, there's only one for each thing. Each belief has two attributes associated with it: the utility and the veracity. The veracity is how true it is. Utility is how much you want it. So you can have beliefs that would be high utility, but they're low veracity. Those are unsatisfied goals. Then there's things that are true that you don't care about. Right? And then there's things that are satisfied goals, and so on.
But could you adjust the threshold depending on the circumstance?
I think that you could, but that would be a meta level kind of thing. I mean, what you're talking about changing the aspiration level, yes. Then the question is that a goal specific thing, and how do you do it? I agree. That's an important issue. Chris? Oh no. Wait, we can come on, get set up.
So on one of your slides, you made the point that if the agent is acting reactively, it makes no predictions about what's happening. That seems as though your cognitive architecture is going to make a very strong prediction. which is that I couldn't be surprised. The agent couldn't be surprised about the consequences of a reactive action. Is that right, or is that not right?
I was talking about this particular implementation. Again, there's this older version of Pug that interleaves planning, execution, and monitoring. And what I have not done yet is integrated this new lower level module with that. Once we do, then no, for sure it can be surprised. But to do that, you'd have to have the processes to make predictions. Right? I was simply saying that there is a version of this where you can run something in reactive control mode, and it doesn't know what it's doing. It's doing it. There are systems like that. Carry on.
Thank you.